asks us to improve the algorithm for finding primes. And there happens to be an old algorithm called the Sieve of Eratosthenes. I butchered it. Apologies. Can't pronounce all the words. But effectively what it does is that it does a slightly different way of looking at it. We start by listing all of the numbers from, let's say, 2 up to 120 or 150, whatever it is. And we actually start marking things that are multiples of the first number. So let's say we start with 2 over here. And then what we can do is that we can go ahead and we can say 2 and then all the multiples. So 2, 4, 6, 8, 10, so on in that list are obviously now primes. So once we've knocked all those out, we go to the next ones. That would be 3. Okay, so we take 3 and all of its multiples. So 3, 6, 9, 12, 15, so on, and we knock those out. Eventually, once we finish all of that elimination process, we're left only with those numbers that are actually prime in that whole list. In great gratitude to Wikipedia, as we can see over here, there's a written out algorithm of what's happening here, because we start out with the list of integers over here, then we start p to equal to 2, we do all the multiplications, we move up, then we go to the next p and the next p to figure out what all the numbers are. So if you are starting out with numbers from, let's say, 2 to 30, you can list them out. Then first you get rid of all of the multiples of 2, then you get rid of all the multiples of 2 and 3, then multiples of 5, and so on, and eventually you're left just 2, 3, 5, 7, and these are the prime numbers under 30. Again, with tremendous gratitude to Wikipedia, we actually have the full algorithm written out for us. This is the pseudocode. And this pseudocode here is something you're going to have to get comfortable looking at when you're doing programming, is that algorithms are often not written in a way that it is literally the code, but it's written something that looks pretty close to code, but not exactly like it. So this is it. Now, this is so clear and explicit that we're actually going to do is we actually take it and we're going to go ahead and translate it right to our code that we're going to be writing. So what we're going to be doing here is we're going to be taking an array of booleans. We're going to start with 2. We're going to start them with 2 squared, and so on and so on. The reason why, I'm going to put the link to this Wikipedia page in my description for the exercise. You can read more about it, but there's an optimization that happens here. But we're going to take this algorithm right here. We're going to translate it into code to solve for finding primes using the sieve of Eratosthenes. Apologies, I can't always pronounce everything correctly. We can now go ahead and move over to actually implementing the sieve of Eratosthenes implementation. So we're going to have a method. We're going to do it again in a method, just like we do with the other prime implementation. So we'll have a standard vector of int. This will be primes up to n. And we're going to go ahead and do the implementation here. We're actually going to need not one vector, but 2 vectors. So the first vector is going to be a vector of bool, and we'll call this just our sieve, and we'll initialize it as empty. And we're going to have a vector of int, and this is going to be our primes. This is going to be our result one. And we'll go ahead and, as we did in the previous method, return primes here to make sure that we wrap up the method and it all has the right structure. So we first start off with like this. For int I is equal to 2, I is less than or equal to n plus plus I, we're going to go ahead and add those values. We're going to do sieve.pushback true. So we're essentially initializing all of the sieve with true values. We haven't seen how to do that initially as a straight initialization for all values when we create the vector, but we'll get there eventually in the course. Now that we have an entire vector full of these values of true, we can go ahead and do the actual core implementation. You will see the algorithm here on the side. This is straight from the Wikipedia page. It's going to be linked down in the description. You can also see here on the side projected, so you can see how we're translating the pseudocode into the algorithm. So we're going to start again for int I is equal to 2. That's where we're starting in terms of the prime numbers. I is equal to n plus plus I. And this is where the interesting part comes in. So we're going to do for j is equal to I squared. J is less than or equal to n. And what we're going to do, we're going to increment j by I. So when it's 2, we're going to move it up by 2. When it's 3, we're going to move it up by 3. When it's 4, we're going to move it up by 4. And what we're going to do is we're going to do sieve at j minus 2. Remind you, right, because what we're doing over here is we are starting off all of our positions shifted by 2, so we need to do it like this. J at I minus 2 is equal to false. And then now that we have this, we know that we have all of the values now marked as false, the ones that are not prime. So what that means is now we just have to populate the final result of primes. So for int I is equal to 0, I is less than sieve dot size. I'm going to go through all of the values, I plus plus I, if sieve at I is sieve at I, i.e. it's true, then what we want to do is we're going to do primes, push back, we're going to need to add I plus 2. Okay, let's go ahead and fix this. This was a small bug on my end, apologies. And let's go ahead and run it now. Let's see what we get. Make sure it compiles. And let's look at the numbers. We got 2, 3, 5, 7, 11, 13, 17, 19. Yep, looks about right. Let's see what happens if we do it until up to 1,000. There it is. So this looks about right. And so these are all of the prime numbers up to 1,000. And we can probably add more, and we can do more of this calculation. Okay, this is the implementation for the Sieve of Eratosthenes. We can go ahead and ship this code.